Everyone. So once again, so sorry for the inconvenience caused by me. Actually, this is the audio recording of the first 5 to 6 live session because due to some issue, the recording due to some of my system starts anyway. So welcome to the 12th 13th live session. This will be a 1 hour session. So in this session, we are going to discuss about what we are going to discuss about the summary that we has been done from the in semester of real analysis. So if you have any doubts, any question, please ask me or let me know. I will try to resolve those. So, yeah. Okay. So first, let's start from the summary. So once again, let me check whether the recording is going. So and also this video will be uploaded to YouTube. So no need to worry about network issues and all. Okay. So yeah. So we have started with the real. So in this real school is through real numbers, where we have discussed about neighborhoods, open sets, closed sets, limit points, isolated neighborhoods, open sets, limit points, isolated point, closure, derived set, then set, perfect set. Then we have gone through the sequence. We introduced our sequence, where we have first got to know our bounded sequence, modern sequence, modern convergence sequence, modern convergence theorem, sandwich theorem. Okay, this sandwich theorem is very very important for your exam purpose. Okay, now there is something known as the subsequence. So due to subsequence, then we have got to know about the concept of limit supremum. Limit supremum are the supremum of limits of all possible subsequences. Limit infimum all possible subsequences. Cauchy sequences and Cauchy criteria for convergence. So these are the very basic things we have got to know in the sequence chapter. Then the series is basically higher application sequence in some different manner. So in series, we have got to introduce about the test of convergence of possible real number. The first, where the some important test are ratio test, root test, comparison test. Okay. So these three tests are very basic tests, and also many problems can be done using this test. Okay. So there is one concept of series of arbitrary terms conditionally. Then we have got to introduce the conditionally convergent series and absolutely convergent series. There is something Abel's test and Rickle's test, which actually used in order to look at the convergence of series of arbitrary terms. And these tests are very, very important for exam purpose. Okay. So then we introduce ourselves with a very important concept of real analysis, limit. Okay. So here we have introduced first the definition, then we have introduced the sequential criterion, then we introduced the one-sided limit, then we got to introduce about infinite limit, and finally the limits at infinity. And also there are one important theorem that limits a modern function. Okay. So then we introduce ourselves the continuity. The first we have introduced as with the definition, then we have introduced the sequential criteria of continuity, then we have introduced the discontinuity of both first kind and second kind. Then we have seen that the sum, product, and quotient continuous function are defined are continuous. Then we have introduced ourselves with the uniform continuity, monotone map, and the continuity over compact space. Well, this continuity over compact space is not important for the exam, but I mean those who are interested has already seen it, and if you're not interested, then you may ignore this continuity over compact because there is some more advanced topic. Then we have introduced the differential. For first we go get to where first we introduce the definition, the higher derivatives, sign or derivatives, some properties. Then we introduce the Rolle's theorem, Lagrange's theorem, Cauchy's mean value theorem, Taylor expansion, and maximum minimum L'Hopital's rules. Problems including Taylor's theorem and L'Hopital's rules are very much important for exam purpose. Riemann integration. Then we introduce ourselves the Riemann integration. First, we have introduced the concept of partition. Then we have introduced the concept of upper sum, lower sum, norm of partition, and also we have introduced the refinement of partition. And finally, we have seen some properties of the Riemann integral maps and the fundamental theorem of Riemann integration, a mean value theorem, and some examples. Then we introduce also the concept of metric space. But first, we have defined the properties of metric space definition and we've done some problems. Then we have introduced the concept of convergence, same as the real and almost same, not exactly. Continue with the compactness. Then we introduce the concept connect. No, no, sorry. We have introduced up to continuity. Okay. Well, there are some two important concepts of metric space which actually completes the metrics of thing. One is connectedness, another is compactness. The point is, if you're really interested in the matrix space realize, then you should go through these two complex kind after your exam. And because this concept creates some kind of actual intuition that why we should know or we should learn the convergence, continuity, and all. Okay. So these two chapters are actually really practically helpful in order to understand definitions, continuity, and the properties of the metric spaces, convergence, etc. and all. So in metric space, step by step, we have learned from triangle inequality, then we have introduced open ball, closed ball, limit point, closures, boundary point, normal spaces. And finally, we have seen some nice spaces, namely LP space, C infinity space, C00 space, C0 space. Yes. Okay. By the C0 means set of all sequence converge zero. The convergence. In convert, we have seen the definition, Cauchy sequence, completeness, density, boundaries. In continuity, we have seen the definition of it and some equivalent conditions, uniform continuity, homeomorphism. So just I think I should tell the books again. So for reanalysis, you should look at the books by Bartlett and Sharbard and look at the books written by Goldbard. And also please solve exercises because solving exercises will sharpen your concepts and you can remember things very clearly. So solving is very important rather than knowing of the theory again. And for the metric space, please follow the book Topology of Metric Space by Professor Kumaration. And also, if you find interest in the metric space by going through this book, then you should look at the book Topology of the Metric Space. Well, this book contains some important concepts of metric space, but also this topology at points of topology is actually generalization of metric space. It's a generalization. It's a generalization of metric. That's why you should go through this topology book by Grace. Okay. So yeah, that's all for the that's all for summary. So now let's do some problems. Okay. So okay. Once. So the so So consider the eliminate. Eliminate means set all those sequence xn such that xn is bounded. That is, eliminate is the set of all bounded sequences. Okay. So here consider the set C00. C0 means those xn which are ultimately zero. Then question is C00 complete? Is C00 complete? So this means what? So this means we need to show that if we take any consequence C00, it is not convergent inside C00, right? So first we so answer is no. So but how to do it? So we need to choose a sequence which is Cauchy but not convergent. Okay. So take a sequence xn. So take x1 to be 1, 0, 0, 0. X2 to be 1, half, sorry, 0, 0, 0, 0. X3 to be 1, half, 1 third, 0, 0, 0, 0, dot, dot, dot. And xn to be 1, half, 1 third, 1 by n, 0, 0, 0, 0. Then the point is that, so point is that the sequence xn is Cauchy since for n greater than m, non xn minus xm, this is equal to 1 by m plus 1, which goes to 0 as in infinity. But obviously xn converges to 1 half, 1 third, dot, dot, dot in infinity, but this thing does not belong to C00. So C00 is not closed. Okay. So that's a C is not closed. So what is the main technique? The point is that we need to find a Cauchy sequence which converges but not inside of that subspace. Okay. So this way we can solve this type problem. So yeah. So there's one problem, and so consider the second problem. Okay. So let me find it out for. So wait for some minutes. Right, so let me find some problem. Yeah. So the next problem is that, mm, so suppose X be a non-linear space. Okay. So show that the norm function is continuous. Or it. Okay. So here we will use sequential criteria for continuity. And remember that we have already seen that distance function is continuous. So similarly, the similar will work for in order to show the norm function is continuous. Okay. So how do we? So let xn goes to x. We need to show norm xn goes to norm x. Basically, consider this thing. So the basic property norm this is less than equal to norm of xn minus n. And this converges to 0 as n tend to infinity. This implies what? This implies norm xn converges to x as integrated infinity. This implies norm is continuous. Okay. So now, so yeah. So this problem can be done this way. So yeah, that's it. So now consider the following problem. So let X be metric space. So A and B are two dense subspaces. about A union B and A intersection B. So the point is that closure of two sets is the union of closure. This is obviously X. So union of two dense set is dense. What are the intersection? So intersection may not be dense. As a counterexample, X equal to R, take A is equal to rationals, B is equal to complement. We know that both are dense, but the intersection is empty. So cannot be dense, right? So that's why the intersection may not be dense. Just a fact. I mean, you can take it as fun fact. Sum of two closed sets may not be closed. For example, Z and root 2Z, Z plus root 2Z is dense. I mean, yeah, this fact can't be proved right now. You need to assume because this proof is something very tricky. Okay, so you can find this proof in the book of Kumaration in chapter in page 52. Page number 50, you can find this proof. Right now, the time constraints are possible to go through this. So, one second. Consider the following problem. So, show that real line and the parabola y equal x squared. So how to prove it? Define a function f by the parabolic graph of the parabola. Okay, so we can define a function f from R to x square t goes to t comma t square. I mean, this is the assignment. T goes t and t square are the shapes. So, so both maths is a homeomorphism. So, okay, there is. So, I think I should tell something which is not stereographic projection. I think I should mention this. So, this stereographic projection. So, what is the stereographic projection? So, let's understand this thing with picture really. Okay, so this will be the last topic of the today's seminar, and this will be last topic for this semester. Okay. Basically, exterior projection gives a map from SN minus North Pole to R. How this is map? How the map is constructed? Consider this R. Okay, and consider the sphere here. Okay, and take the North Pole out. The map is considered as follows: from Sn minus from sphere to Rn, consider as follows. We just take a point X and consider the line that passes through X, and we will look at the point of intersection. This is denoted as phi x. So, how to determine the phi x? So, it's a path, follow this path alpha. Alpha t is equal to, since this path to the North Pole, P of the people. And we need to check fire it x axis. We need to write this thing very explicitly. So take x is equal to x1, x2, xn plus 2. T is equal to 0, 0, 0, 1. So alpha t is equal to 1 minus t 0, 0, 0. This is n plus 1th term plus t into x1, x2, xn plus 1. So this is what this will be tx1, tx2, txn. So 1 minus t. So plus txn plus 1. Means what this thing parts from z equal to 0. It is not x is the z equal to 0. This thing to be 0, what will be our t? So 1 is equal to t minus txn plus 1. So this implies t is equal to 1 by 1 minus xn plus 1. So x goes to x1, x2, xn 0. And we will consider the point in R is xn by 1 minus xn plus 1. This is the map from Sn minus North Pole to Rn. This is one map. So how to construct the reverse map? The reversal can be considered as follows. So again consider this plane and again consider sphere. Let's take the North Pole out. So if we choose any point x here, and if we consider the line with this, then we need to check where this shy. We need to calculate the at which point this line intersects the sphere. While a map Rn to Sn minus single dumping. So how to read? So x is equal to x1, x2, xn, the point in Rn. Okay. The equation of line. So this equation of the line is 1 minus line is tp plus 1 minus ts. Okay. So this implies what? This implies tx1, tx2. We unity constant 0. Txn plus 1 minus t. Yeah, so 1 minus t. Okay. Now we need to check where this thing intersect Sn. So we need to find at which t this norm is 1. So this implies t square x1 square plus t square x1 square. Okay. So this implies what? T square norm x square plus 1 minus t whole square is equal to 1. Okay. So the finally this calculation gives that t will be 2 by 1 plus norm x whole square. And finally this psi, the reverse map is given by psi of x1 is to xn given by 2x1, 2xn, 1 minus norm x squared by 1 plus norm x squared. And it is not difficult to calculate this phi composite psi. I mean, it's not difficult to show that phi and chi are inverses to each other. Okay. So yeah. So this is no steroid projection. Basically, steroid projection tells that Sn minus similar P is homeomorphic to Rn. So this thing tells. So Sn minus a point homeomorphic with Rn. And in topology, there is one notion which is right. It's a generalization of it, known as the one-point compactification. Okay, so now okay, there is one important known as the Ulyssian's lemma. This lemma tells about existence of some kind of functions in a special situation. This lemma tells let A be two disjoint closed sum of. Then there exists a continuous function f from x to r such that 0 less than equal to f less than equal to 1 and f equal to 0 on A and f equal to 1 B. Okay. So so this is the Ulyssian's lemma. Okay, I'm not going to discuss the proof of it, but it's a lemma actually. Okay. So yes. So okay. So now consider the following problem. So let f1 be n and f2 calculate df1 f2. So how to reach? Observe that by definition df1 f2 is equal to infimum of d x comma y x belongs to f1. So now point is n plus 1 by n minus n is equal to 1 by n. This goes to 0 as n tends to infinity. So this implies that df1 f2 is 0. Okay. So we need to realize that the distance is actually converges to 0 for any particular suitable chosen type of element. So that's the main technique here. Okay, so let me find some more problems. Sure. So the next problem, now consider the following problem. So define SON equal to all those metrics of ON are such that determinant of A is 1. So the question is that, so SON are closed in a manner. How to do it? So say as one might guess, here we need to consider this function. This inverse image of a point of subspace is this way. So define a map from ON to R by A goes to determinant F. Okay. F. Then what then? F inverse of 1 is nothing but S square. And this is closed. Here F is continuous. F is sorry. So SON is closed in average. Okay. So now, so comes with the following problem. Well, so let me stress some facts. I'm not going to prove these things. You can find in school the information. RN is complete. CN complete. LP complete. Also L infinito complete. C0 complete. These proofs you can found you can get in any books on matrices or any book of basic function analysis. Okay. So yeah. Okay, so there is one concept of open map and closed map. It's a very important, practically useful concept. Okay, so let f x to y be continuous. Okay. I mean, though the definition actually doesn't mean continuity, but it's better to keep the continuity in mind, in my mind. Okay. So if is open, if if maps. Open map means it maps open set to open set. So it open set to open set. And similarly, it will be closed if it maps closed set to closed set. So by this thing. So there is one important fact which tells that definition of the homeomorphism. Sorry, I mean that homeomorphism. So we have gone through the different homeomorphism which tells that the spaces are homeomorphic if and only if there is a there are two continuous map on reverse on both way, which says that they are inverse to each other. Okay. So the fact is that homeomorphism are both open and closed. Okay. It's not difficult to show because if this is x and this is y and f is a homeoconverse map G. So I mean if U subset of x open, since the homeomorph so fu has to be open in y, right? So this is almost obvious. So homeomorphism implies both open and both, right? Okay. So also consider the following problem. So okay, so we have gone through the concept boundary. So on the following question, what is there? What will be there? Where A is equal to BX. Answer is since del A is equal to closure minus interior A, so del A is equal to BXR minus B of interior. So basically it is the sphere of XI. So means those Y such that distance is this one. Yeah. Okay. So we so consider okay. So now do the following problem. Let D be subset of X billions and F X to R be continuous maps us that F restricted to B is zero map. Then show F equivalent to zero on all of X. So the question reads like that. D is given the dense set and F X to R is a continuous map such that F restricted on A is equal to zero. We need to show F is the zero. So how to do it? Thing is that if we take any x belongs to x, here is a sequence Dn in capital X such that this sequence Dn will converge to x, right? So the sequence Dn will converge to x. Okay. So since f is continuous, so obviously f Dn converges to f of x, right? Okay. So this implies what? I mean, so what is fdn? Fdn will be equal to 0 because it is a given condition. This implies fx equal to 0. So basically here we have used the density since to get a convergence sequence which converges to any our chosen point. Okay. So that's why this function f is 0 on x. Okay. So this is a very interesting use of density. So okay. So well so mm, oh, yes. So I just recall one thing that in the properties of metric space, the one important property that we have learned is the notion of Hausdorffness. and notion of house traffic. So it is a very one important one, practically important property. So I forgot to mention this property. So, so there are some concepts like the equivalent matrices that we have also learned. I just forgot to mention. So that's all for today. So there is nothing really much to say about it. Okay, so practice problems as much as you can. Books. So try to solve jam questions. Try to solve competitive questions. Try to solve some kind of real analysis. Okay. So yeah. Also, if you have any doubt or any issue in my YouTube videos, please ask me through the comment section on over the YouTube. Okay. And all the best for your upcoming semester exam. Meet you soon. So also one more thing I should say is that it's a nice to interact with you guys. Okay. So I've tried my best to teach this thing, history analysis. I hope I can improve my. I mean, gradually I'll try to tell more uh, in the upcoming session of library analysis. Okay. So that's all to the session. Please do problems as much as you can. Also, best of luck for your exam. Thank you. So I'm ending the call here. Thank you very much.